Okay, so I'm going to tell you a little bit about our Levodopa trial that we conducted a couple of years ago. And I realize I'm standing sort of between you and beer or wine, and if you want drinks, feel free to go now. No. How does this, is it not? Okay, I'll just do this. Okay, so I want to start by acknowledging the wonderful team of people that I really had the privilege of working with in this trial. And one of the reasons I decided to put this slide up front is to really show you the number of people it really takes to run a small clinical trial. And none of this would have been, and you can see we have people represented in the room. Lynn is here, Carlos is here. These were all the people who were actively involved in this study, and without whose really hard work, none of this would have been possible. And the reason we were able to really initiate this trial within our consortium was because about 10, actually 13 years ago now, Arbadette and others had come together to form a consortium as part of the NIH Rare Diseases Clinical Research Network. So the consortium was initially funded in 2004. Art was the study chair from 2004 to 2009, and Alan Percy took over from 2009 to 2014. So when we started this trial in the early days in 2010, 2011, we already had the infrastructure in place. So this really speaks to the importance of maintaining brick-and-mortar study sites, having infrastructure, so that if someone wants to do a clinical trial, they can come to us, and we would not have to hire personnel. We just take the protocol, put it through IRB, and we are ready to go. We started with the natural history study. And through this study, we actually learned that there were significant differences, phenotypic differences across various Angelman subgroups. So here are some examples of how the kids could be different depending on their molecular subtypes. So you can see, for example, that the UBE3A kids had a far lower prevalence of seizures compared to those with deletion. Their development was also different. So as you can see, the kids with deletion were more delayed than those with UBE3A kids. And what these data really showed us was the need to think about subgroups when we randomize and conduct clinical trials. And I think this again speaks to the importance of having some longitudinal natural history data, because it really helped us think about and design our clinical trial. So nothing in science, as you know, starts in a vacuum. And before we embarked on the Levodopa trial, we had actually already conducted within the consortium, or at least some members of the consortium had conducted 2 previous clinical trials in Angelman syndrome. Results of which you have heard at previous conferences, so I will not belabor the point, except to say that in the first study was done just before the formation of the Rare Disease Consortium, and it didn't show any difference. That was a double-blind placebo-controlled trial. We subsequently went through an open-label trial as part of the RDCRN consortium, with a narrower, smaller age group, larger number of patients, but again, we did not see any clinical effect. So, at this point, we had sort of thought, well, maybe the whole premise behind these 2 therapeutic trials was that if we activate the paternal copy of UBE3A by giving kids with Angelman syndrome large amounts of methyl donor, that perhaps we could rescue some of the phenotype, and that did not turn out to be so. And I think one of the things we learned was that you really cannot affect methylation patterns very easily through dietary interventions, and perhaps thankfully so. Otherwise, human species may not be alive today. So we sort of decided that we had to take a slightly different approach. And instead of trying to turn on UB3A, which really would be great with a paternal copy of UB3A, and I think that's something that a lot of people are trying to do at this time, we thought in the meantime, can we take a neurobiology approach? So you have heard a little bit about behavioral testing in mice. That's the maze, water maze, and the rotor rod, which are essentially tests of memory and of coordination, respectively. So the scientific basis of the trial really built upon Ed Weber's groundbreaking work that was published in 2007. In which he showed that if you have excessive phosphorylation of a molecule called chemkinase 2 in neurons, you could impact learning. So chemkinase 2 is a molecule that is involved in transmission of signals in the postsynaptic membrane. And there are two amino acid molecules, threonine molecules in chemkinase 2, one at position 286, and this needs to be phosphorylated in order to form memory. So LTP is long-term potentiation, and it's essentially a cellular model for memory formation. And what people have shown in mouse models is that autophosphorylation of this particular amino acid residue promotes long-term potentiation. However, there is another amino acid, another threonine molecule at position 305, 306, and if you have excess phosphorylation of this particular threonine molecule, then long-term potentiation and by extension learning and memory is impaired. And it is believed that you need to have a balance between the threonine phosphorylation at 286 and at 305. So what Ed Weber and his colleagues showed was that in a mouse model of UB3A, there was increased phosphorylation at both the threonine 286 and threonine 305 amino acids. And consequently, chemkinase 2 activity is reduced and long-term potentiation is impaired. However, if they create a mutant mouse in which the threonine 305, 306 amino acid residue cannot be phosphorylated, and you can do this genetically, then they can rescue the phenotype and long-term potentiation improves. So this was interesting and exciting because it basically for the first time gave us a potential druggable target. So this is what they showed in their paper, and you can see that, is that pointer? Okay, so that's wild type, that's the Angelman syndrome mouse. So this is a maze, water maze, Morris water maze, and this is what they're supposed to do, which is to sort of spend time here in the wild type mice, and you can see the Angelman syndrome mouse sort of goes over the water maze. In a chemkinase 2 305, 306 mutant mouse, it behaves essentially almost like wild type. And when you cross this with Angelman syndrome mouse, you rescue the Angelman phenotype. So you can see that this Angelman mouse in which the threonine molecule cannot be phosphorylated, it does not go all over the place. And you can sort of see it quantify that. So this is basically a demonstration, preclinical demonstration of how if you could alter phosphorylation at this particular amino acid residue, you could alter the phenotype. And this basically showed the same thing here. So what was interesting then was that there was a rat model of Parkinson's disease that actually showed increased phosphorylation of chem kinase 2 at 286. There was also, in this particular rat model of Parkinson's disease, increased phosphorylation in a number of different proteins. And Levodopa, as many of you know, is a drug that has been used for over 30 years to treat Parkinson's disease. And what these investigators found was that Levodopa actually reverses the phosphorylation, somewhat non-specifically, I would say, in some of these proteins. So the question to us we then raised was, if we were to give Levodopa to children with Angelman syndrome, can we reduce some of the excessive phosphorylation in chem kinase 2 and therefore rescue the phenotype and improve development? So Levodopa has to be taken with carbidopa basically to reduce the side effects, but the prodrug here and the active drug is really Levodopa. So that was our hypothesis, that if you gave children with Angelman syndrome Levodopa, you could reduce the phosphorylation, improve the neurological deficits. And there had been some anecdotal evidence that perhaps this would work. So there were 2 adult Angelman syndrome patients, I believe from Australia, who had Parkinsonian symptoms, and it was reported that when they were given Levodopa, their tremors improved, which is not surprising because that's the drug used to treat tremors in Parkinson. And we had also surveyed parents of children with Angelman syndrome and found that there had been, at least anecdotally, some suggestions that it could help. But the problem with anecdotal evidence is that there were different parents using different doses, different for different periods of time. So there was really, it was hard to know just from this alone whether or not it really worked. And some parents say it didn't work. So we decided that the only way we were going to do this was to conduct a clinical trial in a controlled setting to answer the question of whether it worked. Now the problem was, of course, was that no one had ever used Levodopa in the Angelman syndrome population in a study, so people have used it anecdotally with varying doses, and we had to decide what dose to use. So we conducted a dose tolerability study, and this took a lot longer than we thought. So you can see we started this study in January 2009, completed only in June 2010. I will say that when I started this study, I thought we could get this done in 6 months to a year, and it took us 18 months before we collected enough data. It was a standard 3+3 design, which is what the oncologists use to do standard dose finding studies in those populations, and we felt that was a good model to use. And we had to use a compounding pharmacy because we had to dose kids by weight, and Levodopa only comes in 100 milligram tablets, so you couldn't dose it by weight if you didn't compound it. So this was what we found. After 18 months running a dose-finding study, and you can see that we went up. So I'm not showing you the data from 2 milligram per kilogram dose because those Levodopa levels were sort of just really low. That was basically homeopathic. Our target range for Levodopa concentration was between 1 and 3 milligram per microgram per mil. And we had chosen that because that was the therapeutic range for treatment of Parkinson's disease. Now, is there a reason why we chose that over any other range? No, but we had to start from somewhere, and it seemed reasonable that if it worked for Parkinson's disease, that perhaps it would work for this, given that the presumed mechanism was the same. But you can also see that we had kind of variable concentrations even within the same dose for reasons that are not fully understood. Nonetheless, we met with the DSMB and they decided that we should start with 15 milligram per kilogram per day. So we then went on to design what we call the phase 2 trial. It's really a phase 2B/3A trial. of levodopa, randomized double-blind placebo-controlled. Our target was to recruit 100 participants over in 7 study sites, 6 of which were the existing natural history sites. So again, we built on the infrastructure that we already had in the natural history study. And because the natural history study had taught us that there were significant differences between kids with deletion versus non-deletion in terms of their phenotype and developmental outcomes, we decided we had to randomize them in 2 different subgroups to ensure that we did not inadvertently recruit more deletion or non-deletion kids in either the placebo or the levodopa group, which would skew the data. So again, the initial plan was to run the study for a year and then have an open label phase so that everyone who came to the trial had the opportunity to be on levodopa. We had a step up and we decided that you had to be on at least 10 milligram per kilogram per day in order to qualify for the study. So if you started at 15, you had some side effects, we could bring you down to 10, and if you had more side effects, you had to drop out. Those are our primary outcome measures. So again, when we started, we said, well, 100 participants, we had a lot of enthusiasm, and people said, yeah, you can recruit 100 subjects in 6 months to a year. Look at how long it took us to recruit 78 participants. So it took us more than 2.5 years to recruit 78 participants between age of 4 and 12. It's actually 4 and 13, so they were allowed to come in as long as it was before their 13th birthday. Of the 78 participants, we were able to treat 86, so some of them, 67, so 86%. Some of them screen failed because they had poorly controlled seizures. There were some parents who came to the initial baseline visit and decided at that time that, well, actually we don't really want to take part in this study after all. And then there were some who did not show up. You know, the coordinators would call them, they said, yes, we are coming, we are really interested. We gave them a study number, and on the day of the visit, they just didn't show up. So those were the reasons, you know, so we had we lost 14% of the participants right there. And bear in mind that this was actually a relatively straightforward study from a parent's point of view. They just had to come once a year for one visit, so a baseline visit, a 1-year visit, and to take a pill 3 times a day, nothing else. So out of 67, we randomized 34 kids to placebo, 33 to levodopa, and you can see, interestingly, that a larger proportion of individuals in the levodopa group actually completed the trial compared to the placebo group. Now you would ask, why is that? So people had asked us, why do you need a placebo group? Why don't you just give everyone levodopa, see whether it works? And if you have side effects, then you know that you have to be on levodopa, right? Because it's placebo, it's a sugar pill. Well, so we had reasons for study withdrawal. So placebo group, 24% failed to complete. We had 5 adverse events in the placebo group. Get that, right? And of course, we didn't know they were in placebo. All we could tell was, you know, it was double blind, and it was really important it was double blind because we didn't know, parents didn't know they were on placebo. They had all these side effects. We were convinced, the parents were convinced that they were taking active drug, and then therefore they had all these side effects. But that's what we found. That's the data. And then we lost 5 patients to adverse events, and we lost 3 to non-compliance. Some of them just stopped taking the drug and decided it wasn't worth the pill. Now the other point I would note is, one parent decided that they just couldn't manage this. You know, and one of the things to remember, I think, as we move into clinical trials in this population is many of these kids are on a ton of pills for seizures, for constipation, for all kinds of things. And now you have to add study pill as well. I mean, that's a lot of medications to juggle. And some parents just found it difficult. Now, look at the levodopa group. So we lost 4, 12%. We had 1 adverse event. 1 dropped out because of adverse event. I'll show you the full adverse event in a minute. And then we lost a few because of, so one felt that he was unable to take medication 3 times a day, and then there were 2 who just were lost to follow-up. So that's the entire cohort. And as you can see, if you look at placebo versus levodopa, you get approximately equal numbers of proportion of males and female, deletion and non-deletion kids. So this basically showed our randomization process worked. We were not necessarily biased towards one molecular subclass or the other. And you look at the total number of adverse events. So what I had shown you on previous slides were adverse events that led to study withdrawal. These were the total number of adverse events. And these numbers are much higher than the number of kids because there were a lot of kids. There were some kids who had multiple adverse events. But the point here is that if you look at the placebo group, a lot of them reported adverse events. And if you look at proportion, you can't really take a true proportion, but you can see that proportionately there were not that many more adverse events in the levodopa group compared to the placebo group. So we found this really instructive, at least I did, and it really brought home the point of the importance of having a levodopa group. Okay, so this is a terribly busy slide, and I had to do it this way because this is the only way you can really understand. So our outcome measures were essentially developmental outcomes. So Bailey, Vineland, and aberrant behavior checklist, which is sort of behavior. And you can see, if you look at the placebo group first, I'm going to use my mouse if I can. Okay, so what this shows you is that, okay, you can see if you just focus on the Bailey for a minute, you see that these are the baseline scores, these are developmental ages, and this is what they had at 1 year. So over the course of the year in the placebo group, this was how much they changed. So very little slight improvement. In the levodopa group, this was their change. Okay, well, I'll come to this in a minute, but just focus on this column. So it says gain in 1 year, so this is how much they gained. So you can see that the kids who were in the levodopa group really didn't make much developmental gains other than their their gross motor skills. Now, this is something called generalized estimating equations, and what it really calculates is delta of delta. So it's the difference of the difference. And the reason you have to look at this is because we know that Angelman syndrome is not a regressive disorder. Angelman syndrome kids progress in development over the course of a year. And if you just look at changes from 1 year to baseline, you're going to see a change even in placebo group, as you see here. So the question is not, is there a change? The question is the change greater in the levodopa group compared to the change in the placebo group? And this is what this number really tells you. This is difference is the change in the levodopa group compared to the change in the placebo group. And this shows you the magnitude. So you can see for the most part, there really wasn't anything. So if you look at the p-value, there really wasn't anything, no change in the Bailey. So really convoluted way of saying that, at least in this population, in this study, we could not demonstrate any changes in the Bailey scores over the course of a year. And if anything, the levodopa group did not improve as much as the placebo group. When you look at Vineland, which is basically parent report of development, again, you see the same trend. And you see and it's interesting, and I don't have a good explanation for this, but some of the Vineland scores actually dropped, albeit by very little. It's not clinically significant, but it is a decline compared to the placebo group. Now, what's somewhat more interesting is when you look at behavior. In the aberrant behavior checklist score, the higher the behavior, the more problematic. Right? So your ideal score is to get this down to practically nothing, or really low number. A high score means you have problems in this domain. So basically what this showed you is that in the levodopa group, it looked like for stereotypy and to a lesser extent irritability, there seemed to be some improvement in the levodopa group compared to the placebo group, but there was no change in hyperactivity. If anything, well, there was a slight decrease, but it wasn't statistically significant. So basically, we concluded that levodopa is relatively safe. So when you look at placebo versus controls on the levodopa group, there was no difference between the side effects. But at least over the course of a year, there was no statistically significant difference. ABC, possibly something to think about for future trials, but otherwise, we would not, based on our data, recommend the use of levodopa. And finally, I just want to thank all the people who were involved in this trial again, as well as our funding sources, including ASF, and Lindbergh, from whom I stole many of these slides. All right, 5 minutes over.
Questions?
I think you all want alcohol. Yes.
So, looking back,
Yep.
what do you wish you'd chosen different outcome measures?
No. Well, no, because the premise of this trial was that levodopa could improve development, and those were the best available developmental measures we had at the time of the trial. Now, do I wish we had better measures and more sensitive developmental measures? Certainly, but that was just not available to us in 2011 when we started this trial. Yes. We did. It was very hard to quantify, so I'm not showing the data here. I think it kind of helped a little bit for those who had some tremors, but it was sort of variable. The problem with tremors was that we did not have a good validated scale to measure them. So some of the scales, what we found was that we used the Parkinson's disease scale as a measure of tremors, and they were not sensitive at all. So that was a problem with the outcome measure. Yeah?
I saw that it looked like your Levodopa group actually started out, I can't remember which measure it was, maybe it was the ABC, that they started out, it looked a little different from the placebo group. Do you think if you had stratified the kids into severely affected versus mildly affected, you would have had these differences, or do you think it just wasn't, it just not working?
I think it's hard to tell. It could have. I think the problem then was a matter of study design. How do you stratify? Because we had to stratify as it was by molecular subclass. If you're going to stratify by a second layer by severity, you could then end up with really small numbers. You know, as it is, we only had 24 people in the 24 kids in the placebo and 28 in the levodopa for the ABC.
Are these all deletions?
No, this is mixed.
So these are not stratified?
These are not stratified. We are in the process of looking at deletion alone. We couldn't look at only the non-deletion because, as you can see, in placebo we only had 6 non-deletion kids, and in levodopa only 11. And you know, you really can't do any statistical testing if you have fewer than something like 15 to 20 kids. So even within the deletion groups, we are sort of at a lower limit. I mean, we will do some preliminary, some analysis there, but that really is pushing the limits of what you can do with statistics. So that's, I mean, you know, I think that's the challenge in any rare disorder and conducting clinical trials in rare diseases. And as you can see, I mean, 2.5 years it took us to recruit 70 subjects, and this was the number of participants we ended up with. Any other questions?